Okay, so chapter 3 is measurement and tolerance. The author used the plural for tolerance, and there's an S at the end, but you can also use just a tolerance for plural. So it depends on how you take it as countable or not countable. All right, geometric dimensioning and tolerancing. The short form is GD and T. So GD and T is dimensioning and tolerancing, and it binds design, product, where's my pointer, and part inspection. Okay, and we use it especially in manufacturing. It's kind of like this. It's kind of like a method, okay, a system of measurement that we use. One is we already know dimension, and the other one is a tolerance. Every time you measure something, you're gonna get a value, and then that value is usually expected to be within a range of a tolerance. So if the value that you measure is out of the tolerance like that, it's not very good measurement, okay? Because the accuracy is going to go down. So we use GD and D to bind the design, okay, product and inspection, part inspection. So it's just a set of rules and then symbols. And you will see these symbols on a drawing of a product design, function and relationship, okay, of the part features that will be manufactured. So it's a technique that we use, or a routine, okay, inspection that we use in manufacturing of a product. And you usually use the drawing of a design because you need the design to manufacture a product. And you will see the rules and the symbols, okay, come with that design, which is contributing to the function, also the relationship of the part features of that design to be manufactured. And we use this GD&T rules and symbols to do that. Okay? So it's kind of like make sure that you design the product and the inspection of the part features, they're all giving you the same or okay, measurements. Measurement got to be accurate. So therefore, we need these rules and symbols, okay, to go with it. Tolerance. So tolerance is nothing but what is good enough for a measurement. So we usually have a range like that. So this side is going to, again, direction minus, going in this direction. So if your product design measurement, okay, the true value is this much, we expect your inspection measurement or your comparison measurement to be within this, okay, tolerance. I'm going to use a different color here. Within this tolerance zone. We call this a zone, okay, this area. So everything that you measure, if it is going out of that zone, like on this side, it's not very good, okay? So there's a range from here to here, let's say. So of course you're going to have a value right there for this zone. Again, term, we call it tolerance zone. Go in this direction, plus, getting bigger, the value is. Go in that direction, minus, the value is getting smaller. We apply to both position, okay, where also size, how big the dimensions. Okay, this is just showing you the example of what tolerance is on the picture. It'll be a little bit difficult for you to be able to see it. So what we're doing here is we're drilling a 1 millimeter hole. If you drill a hole, you're gonna have like that, right? And then you drill down and then bang. So the hole itself, the size of the hole is 1 millimeter. And you draw it on the left image. So this size of the hole is 1 millimeter. Okay, so here is showing you like a little cross here and a square. So what we're trying to say is the diameter of the hole. In this example, we're drilling is 1 millimeter, and the tolerance for that, okay, size of the hole is you can go, okay, 1 unit off of that. So you can go 1 unit over and 1 unit under. So this minus mean like going smaller, and that's going bigger. So therefore you have original 1 millimeter hole. You can go plus 1 millimeter, and another going down that direction minus 1 millimeter. Okay? Again, don't feel bad to look at the direction of the value. This is just showing you like you can go this side, okay, 1 millimeter. You can go that side 1 millimeter. Okay, and here is our tolerance zone right there. So it's all right exit. Okay, here is my hole, 1 millimeter. When you drill it, you might not be getting it right there. Okay, it might come off on that side or on that side. Whichever direction you're going, you can do it so, okay, within 1 unit over and 1 unit under. Yeah. So here, let's say the size of this, okay, this one, this side and that side. It's 20. Okay, you can go 1 unit up or you can go 1 unit down. Yeah. It's maybe a little bit difficult for you to take a look at it. You might think like this from here to here is 20 because it looks like that anyway. Okay. What we're concentrating in, so I'm gonna just go ahead and draw it for you. So let's use a different color here. So when you drill, you get a circle like that, bang, with your machine drill it. Okay. So sometimes your drill won't be there. Okay, it might be like a little bit off to that side like that, or you might get it like this size. So whatever that is, you can go all around 1 millimeter, okay, off. So anyway, so now you get the idea of tolerance. So again, this minus, okay, and plus unit for your tolerance value is on the x-axis and also y-axis. So you have to imagine your x, y, z axis. So here is your x, and this is your y, usually here, and then your z is there. Okay. If you draw a 2-dimension, probably like this. So you have x right here, and then you usually have y right there. If you draw 3D, y is usually on this side. Okay, it's kind of like flip, and then your z is in the center. For 2-dimension, I'm going to write this down for you. It's going to be like this. For 3-dimension, is y is now laid, okay, on the this plane instead of that plane right there. Try to get that. So again, you can, okay, have plus or minus 1 unit on x and y axis. So just this, okay. So here is 1 for y, and here is plus or minus 1 for x. And when you look at the diagram, be very careful what you're reading. So you got to read very carefully here. I'm going to draw this out for you, 1, and then here is another one, see? So usually student, when they look at this, okay, tolerance, they imagine only one value right there. It isn't. it is a set of value going one direction, another direction, meaning like you can go off this way and off that way. Okay. The first set is on the x-axis, which is this one, and the second set is on the y-axis. Okay, so you have different grade, right? A student, B student, C student, D student. If when you read it, you're reading the same sentence, okay, but your concentration, okay, most of the time will get only this number in your head. Then that number is just one set. When you continue to read, you're dealing with two different sets of the same number, okay? One is on the x-axis and the other one is on the y-axis. So don't read carelessly, okay? You have to read it slowly and know that what is it telling you, okay? How should I say this? Understanding what you're reading is different from just reading it. Okay, so you have to think with it and go one word after another so that you know you're dealing with two x's and the sets of that number is on each axis. Okay, so therefore now you can get. So if you have only one set, it doesn't make sense. Why? Because you're going to have only two direction. Yeah, you have to have two sets in order for you to have four direction, and these directions are going this way and then that way and this way. See, now you have a circle right there, diameter. If you concentrate only one number right there, see, you will have only linear direction going that way and this way. Okay, if we go more precisely, okay, this is more precise if we go 3 dimension, but here we have only 2 dimension, so therefore we don't have the z-axis, but there is another axis, okay, z-axis going this direction and that direction. See that how different everything is. So in this way you will have like 3 sets with 6 different directions. This one is 2 sets with 4 different directions. Okay, so therefore your drill can go this way, or that way around there. Yeah, the perfect is going to be right at the center of the cross. But we're not perfect, so every time you drill, you're going to get here. Sometimes you're going to go off a little bit. So therefore, when you take a look at your product, they're not the same, right? So let's say, think about a chair or something. You open the box of that chair, you're going to see, okay, the drills are different. They're approximately around where it should be, but they're not exactly where it should be. It's always a little bit off. But of course, with the natural eye, it's not that obvious. Okay? If the points are obvious, then it will go into defect, and we will eliminate them. Okay. So anyway, you got the idea. So there are only 2 sentences here, but a great deal of meaning. So don't just like read it. Try to understand what you're reading. All right. So let's go to the next slide. Okay, so here in this diagram, this textbook it uses many diagrams, so you have to concentrate in what you're looking. Okay, so here is a little A right there, and that point is right here in the zone, right? And that zone is shaded with lines. And when you take a look at another picture, you're going to see here, okay, and this zone is drawn as a square and it is white. Yeah, so you're seeing 2 different shades. One is white, the other one is shaded area lines, and there are 2 points right there. The very first one is here, the second one is right there. Okay, they're not in they're in different location on this diagram. So the first location with this shaded area, and we call that, all right, that area, you can also use zone, and we call the permissible area or permissible zone. In other words, we use functional tolerance zone. Okay, meaning like your drill can go here and on here, on there, on there, and on there. This is a very exaggerated, okay? It's only a 1 millimeter size, it's pretty small. So anyway, when you drill it, sometimes that diameter will come off of this area and then land on here or here or here and here. That's all right, okay? Why? Because it is still functional, yeah? And the product will not get affected. If your drill point goes off from here to here, that's fine, yeah? So therefore we call that permissible area, this area right there. So another area, the white area in the square, is a B point, is right in there, and we call that the true tolerance zone, okay? And this is true tolerance zone because it's giving you the exact one, okay, unit. See, 1 unit, x-axis, and then y-axis, yeah? So if your drill goes right in this area or zone, you're pretty good, right? Near perfect. You can go off a little bit here, 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 here. In that case, you will be in the permissible area or permissible zone. Okay, now we're going to switch the shade here. See, we shaded here, and then you can see that it's just showing you a different contrast, but it's the same thing, okay? And do not forget what you're seeing. So when you look at the square, you see 4 different little squares inside of a big square. See that? So the 1, 2, 3, 4 little square, and that is your x, and that is your y. Okay, going up is positive, and going down is negative. Just showing you the direction. That's 1 plus 1 on y-axis, minus 1 on y-axis, plus 1 on x-axis, minus 1 on y-axis. Okay, so based on last semester, I thought that because this is a middle school and a high school student mathematics, high school mathematics, but some student I think maybe forget about it. So I'm gonna give you a review. Okay, so here this is your x, this is your y. We have only 2 x's. We're considering on 2 dimension. Okay, diagram, 2D diagram. This is a flat, totally flat diagram. So every time you deal with 2 x's, you have direction. So we use a little symbol, mathematical symbol, okay, plus and minus. Plus and minus are not always value, okay, they're just showing you in which direction you are going, okay, from the center point or reference point or origin, we call this one. Yeah, going this way, positive. Going that way, negative. Yeah, it isn't the value. Going this way, positive, and going that way, negative. So now you can see all of that. Plus 1 here, and then plus 1 there. Okay, and then minus 1 here, and then minus 1 here. Okay, so this is a minus going that direction, going this direction, up and down. Okay, this is to the left and to the right. From where? From the reference point starting right here at the origin. Okay, so make sure you know what you're looking at it. Don't just like look at the shape and try to remember what they are. So anyway, true tolerance, because it said it so. Okay, the tolerance is plus or minus 1. Okay, and it is on the x-axis, it is on the y-axis. That's what it said, yeah? So therefore you have 4, right, direction you're dealing with. Going to the left, going to the right, going up and going down on 2-dimensional space, okay? All of us are in the space, so don't forget that. Location, position, taking a physical thing in a space. And as soon as a physical thing is taking a space, okay, taking a place in the space, okay, you start the activity, just being there, okay, just being there, and that's the starting point of the activity, and we call the starting point of time, T-I-M-E, okay. Time is not the, I don't know, some student imagining something weird. Time is nothing but you're just looking at the activity happening in a space, and you have a physical matter, okay, right there. We also have a different nature of time for the anti matter, because our nature has okay, direction. So we have something that is physical, so we also have something that isn't physical, okay, on the opposite direction. So anyways, as you study physics 1 and 2, you're going to get into that directions, and you have to link everything all together. Don't just stay in the world, okay? There's another nature that you need to know, and that's only exists in the understanding of these things, weird thing, okay? But once you get it, you're okay. So once you master how to read the numbers, how to know the direction, how to interpret what you're reading, you're good to go, okay? So see like how different that is just by looking at the picture. You know a great deal right there with this little 2 number and 2 x's, okay? So try to get that sense out of that. All right, so now I'm going to erase this and so put everything right there. Okay, here we go. So video lectures are it's just same as we're using the PowerPoint as a board to write on. Yeah, it's the same thing. Same thing as coming into class. Okay, so now on this slide, we're gonna really take a look at for drilling a 1 millimeter hole. So here you can see the tolerance zone, and that's our square with okay, this we already know that's 1 millimeter. Okay. So when you take a look at this line, that's the diagonal of that square, and we call that the greatest allowable variation for the center of that hole. Okay. And when you draw a circle, okay, across all that 4 points of the square, we see that this diagonal of that square is actually the diameter of this circle. So if you want to get the distance of this line, all we have to do is use the Pythagoras theorem. Yeah, square this, and then square root it. So you're going to get the distance of that. So that's what we're doing here. And 1 here, 1 there, we square them, add it, and square root it. And you'll be getting 1.414 millimeter, and that's the distance of the diameter of this square, which is actually the diameter of the circle, okay? Diagonal of the square and diameter of the circle. And we call that the functional tolerance zone. Okay. Alright, now let's cut that diameter of that circle and divide that by 2, and you're going to get radius of that circle. The same thing, we already know the distance of that, which is 1.414 here, and we're going to divide that by 2. Okay, so you get 0.707 millimeter for the radius right here, from here to here, okay? And if you want to get the area of the circle, all we have to do is use that radius we already calculated, okay? Square it, and then multiply by pi. Pi is 3.41416. If you use a calculator, you don't have to put this, just there's the right button for pi, and then multiply with your r square, which is 0.707 square, and you will get 1.57 millimeter the whole square. Yeah, and we already know this is 1, and then this is 1. Yeah, so now we get the area of the entire circle. Okay, that's 1.557. So the area of this square right here, okay, is going to be 1 because its side is just 1. Area is nothing but you multiply the length and the width. So 1 times 1 is still 1 anyway, but the unit is going to be millimeter square, okay? Millimeter square. So this area is 1, the entire circle is 1.57. So therefore, the area of this blue shade right here, okay, is going to be 0.57. Okay, this one right here, 0.57. That area, the little blue area right here, little blue area. Okay, we're subtracting this one out of the circle area 1.57. So you get 0.57. Okay, 0.57 millimeter square for this blue area. Okay, so that 0.57, you're going to translate that into percentage, and you'll get 57%. Yeah, and we call that the functional tolerance allowance. And we can see that pretty clearly. And this guy is your diameter. We use this little symbol, okay, y. 1.414 is this distance right here. And that's your diameter of a circle, and it's going to allow you 57% of the functional tolerance. Okay. So I think you can be able to see that clearly by now. So let's take a look at, just want to point out, based on last semester, read very carefully, okay, there's a functional tolerance, okay, here too, functional tolerance, yeah, the zone is actually equal to the diameter of the circle, yeah, which is the distance of the diagonal of that square, which is this guy right here. Okay. And that's gonna, it's just the other, I don't know why, like, this author for this textbook write that way. So if you have to pay attention for these things. So anyway, so functional tolerance allowances, we're talking about this blue area right here, okay? These one right there, right there, right there, and then right here. That's only 57% because this guy is 1.0, okay? This guy is 0.57. From your calculation right here, that's the whole circle. So we can see the whole circle is 1.57, okay? And the square inside of the circle is 1, okay? So therefore, 1.57 minus this little square right there, 1, is going to give you 0.57, which is 57% difference. And we call that the functional tolerance allowance. Okay? In other textbook, you're going to confuse. In other textbook, we use this blue area, the functional tolerance zone. I don't know why in this textbook, I don't know, that's a mistake of the author or whatever, diameter of the circle. So don't get into that, okay? So anyway, so now we get into the area of the square. I already told you about that. That's just 1 millimeter because each side is just 1. The geometric tolerancing is going to give you 57% allowance. Okay, what's the meaning of that? Meaning 57% increase in the allowable tolerance for diametrical, which is your circular functional tolerance zone. Okay, right here. So in common words, what it's trying to tell you is when you drill 1 millimeter hole, okay, the ideal location should go into this square, but you can go over that square and land your little hole up to this circle, alright, and we call that the functional tolerance zone. Because if you review your physics, right, when you drilled, you're using an instrument and you're applying a force, okay, with a pressure. So force on area is called pressure. So force is nothing but this is your instrument going down with mass and in acceleration in this case, or drilling down. So your mass, your instrument, and then your acceleration A, okay, which is your force. In this case, this A is a G, which is gravity, okay? So since you're drilling in this direction and making a hole right there, okay, if you go over, all right, if you go over this tolerance zone, which is your square, your hole will always be bigger, all right, than that because you're drilling down, so the forces and pressure is going downwards, so you can never have a smaller hole, right? And your hole will either land here or like that or like this, whatever that is. You can go beyond that square, okay, that can't go over that circle. I think you kind of get it. Yeah, and don't forget your physics. So every time we say we're drilling a hole, that's what we're doing. Applying a force directly along the line of gravity. Okay, let's go on to next. Then we'll come to datum, right? Planes. Alright, so before that, we should know some terms. The very first one is called feature. It's nothing but just a physical portion of a part, okay? And go slow. So you have a part. We're dealing with physical portion, okay? And features are generally, we call them part surfaces, okay? Nothing but surface. So we have like the 1, 2, 3, 4, 5, 6 surfaces on this rectangular block, okay? So feature, if you take a look at the feature, every time you see this term, you know that just a physical portion of a part, especially the surfaces. Okay, the next one is datum. Datum is theoretically, we're talking about either a plane, a point, or an axis. Okay, so plane looks like that. Okay, a point is just a little point like that. Axis are your x, y, and z axis. This is only 3. We have more than 3. Okay, from which dimension is measured. Yeah, you're gonna measure, you get a value. Every time we can measure from a plane, a point, or an axis. You're gonna measure from here along that axis. You're gonna measure here from this point. You're gonna measure, okay, from that plane. Okay, so that's what we're talking about, and that's, we call that a datum. Datum is nothing but a plane, a point, or an axis. Okay, and we're measuring something from them. All right, as location. The next one, datum, feature, datum and feature. So it's a part feature, okay, and it contacts the datum. Part feature is going to contact a plane, a point, or an axis, okay, from which the dimension is going to be measured. So it is used as the origin and for measurement. Okay, so we call datum feature. We are using as an origin, okay, for the measurement. And your part feature is going to be in contact with that datum. Datum reference frame. Okay, so datum reference frame is a big word. It's nothing but these planes, okay, it's a set. We have 3 of them. Mutually, they're perpendicular, meaning like 90 degrees to each other. Okay, so you can see here in this picture, that's first, second, and then a third, okay, planes. So we call this here first, second, and a third, or primary, secondary, or tertiary datum planes, okay? And they are again 90 degrees to each other. Oh, perfect, perfect. planes. Okay, I think you got an idea of what features datum is, datum feature is, and datum reference frame. Student gets these three very easily. Okay, they got issue with this thing. So when you study, make sure you try to get this. I don't know why. This is pretty easy. Well, it's just like a part feature. That part feature is going to be in contact with one of them. Okay, either plane, a point, or an axis. And we use that datum feature as the origin to measure something. Okay. All right. So I'm going to go ahead and erase. Don't try to get everything by heart. Okay. Try to get its meaning or what they are physically. Okay, so we have form, profile, orientation, location, and runout. So these are just the 5 types of control. Okay, dimensioning control. Control means it's nothing but tolerance. So when we say tolerance, right, when we're measuring something, then your measurement got to be, already told you about that, got to be within a tolerance or a limit. Can go over that. So if you go over the tolerance limit, okay, then your dimension is not going to be, or your measurement is not going to be perfect. So that's the reason why your measurement got to be within the tolerance zone. Okay, and since measurements is always dealing with geometry, okay, you're measuring either a straight line or a circle or a rectangular thing or whatever you're right measuring. Sometimes they've got angle, sometimes they have some sort of location. Okay, so whatever you're measuring, it's always okay of a geometry, a particular geometry. So therefore, the tolerance, right, the limit for these measurements, they have particular tolerance, all right, depending on that geometry. And we call them character, right? Characteristics of that tolerance. So now we divide the tolerance into 5 different types, and that's we call them the measurement control. So all your measurement got to be within, all right, within these tolerance limit. And we divide that into 5, and that's first one is we call that form. Any kind of form. It can be straight, flat, circular, or cylindrical form, right? And if you measure, let's say, go ahead and measure that cylinder shape right there. So your tolerance zone is going to be along that, all right, shape. It might look like just like that cylinder, and we call that cylindricity. Okay, and we're gonna give a little symbol like that. So it looks like a little cylinder, you know, a small cylinder like that, cut out kind of form. So anyway, so we have 5 control, and we call that types of tolerance. Depends on your geometry. So the very first one is form, and your characters are straightness, 2 of them, one axis and the other one is your surface. Flatness, circularity, and then cylindricity. And then we have profile, okay, profile of a line or profile of a surface. And we have orientation, angularity, any angle. And if you have like a perfect 90-degree, that's your perpendicularity. And if your lines are parallel, okay, you have a parallelism. And again, we'll go ahead and measure this one. What is my tolerance limit? So you might have a tolerance a little bit, okay, off of that or deviated from that shape. So here, oh, that's my tolerance. Anyway, so that would be parallelism, okay, orientation, tolerance, okay. And anyway, you can see that more and more later. So since we're dealing with measurement of many different geometry, our tolerance type also depends on this geometry. That's the names, okay, form, profile, orientation, location, and ran out. So right now, don't feel bad about it, just try to pay attention to all of that symbols, like I said in the beginning. And ran out, okay, it's nothing but you see here. Location is pretty easy. Your GPS, see this little position symbol, and then concentricity, and then this your symmetry. Okay, I have studied a great deal in symmetry. We used to draw with hand long time ago in my professor time. Now we deal symmetry with technology. Okay, and it's a circular runout, it's like that, and then total runout is like this. Runout is just trying to show you, okay, how much one given reference feature or features vary with respect to another datum, and you wouldn't be able to know right now. Okay, it's just like when the part is rotated 360 degrees around a datum axis. Okay, we already know a datum can be an axis like that. Okay, so when you think about 360 degrees around, we're dealing with a runout, and since it is a 360 degree around, it's usually a control of a circular feature, but don't confuse with the form, right? Circularity. That's more basic than that. This circular runout right there. And we also have a total runout. So we're dealing with a runout is like we're dealing with a rotation, okay? We're dealing with rotation. Rotational axis. And again, don't worry about anything, any deep meaning right now. Right now, there are 5 types, okay, of tolerance, and we call them control, dimensioning control. Commonly we say control, what's your control, what's your control, meaning like your measurement got to be within that, all right, limit. Okay, so next one. Modifier. We have different modifiers, and we have 3 of them here. The very first one, okay, is maximum material condition, and abbreviation MMC. So if you see, you know that's the maximum material condition, and your symbol is M. Okay, close it. Then you have your least material condition, LMC. Your symbol is L, right? And you have RFS, that's your regardless of feature size. Okay, it doesn't matter what the feature size is, and we're gonna modify according to whatever it's saying. RFS, it doesn't come with a symbol. So if you see MMC, we're doing a maximum material condition. If you see LMC, we're doing a least material condition. So what are we doing? We're doing modification, right, to the material conditions. The material conditions modifiers, there are again tolerances at various part sizes. Okay? Don't lose contact with your physical thing, okay? You're measuring a part or you're inspecting a part in a manufacturing facility, okay? Usually metrology is for inspection for quality in my field. So material condition modifier, this one, we use them, okay? That's it's again for tolerances, okay? Why does it matter? Because all parts are made of elements, okay? Elements. So your chemistry periodic table, okay? We know pure elements are pretty expensive. So for manufacturing, all of the parts are all alloyed or mud or mixed. Okay, so depends on that material. Okay, material or material condition. We use different modifiers. Okay, and the material condition is so important. Okay, to come up with a tolerance limit, because they can do expansion also. Okay, when it's hot, then the material expansion is going to be varying. Okay, they vary. So if you have a measurement from here to here is one value, when they are subjected to extreme temperature or something, then you're going to have variations. Okay, whatever the variation is, these parts got to be within the tolerances, right? Considering all environmental factors with that part feature and also the material condition. So it can go maximum, it can go minimum, okay? It can also go regardless of the size of that feature. Okay? Anyway, right now just get in touch with the material condition, and we have modifier. We call them modifier, okay, for this condition. Why? Because they are critical. These conditions are critical for the tolerance limit. Okay? So they can expand or constrict. Alright, next slide. So modifier, we're using MMC, maximum, yeah? Material, MC is just a material condition. If you see M, just remember that's the max. We just say like max, okay? A hole at max. So internal feature of size. Your diameter, that hole, okay, is 6.25 inches. So when you take a look at the hole, and if that is at maximum, alright, material condition, we say the diameter, okay, of that hole, smallest allowable size. Okay, so here in this picture you can see. So it's telling you if you have a condition, internal feature of size, meaning internal feature, the inside, okay, measurement, and that hole got to be internal. The hole is going that way, yeah. So you can have a circle right there. So you're looking down like that, and you see this. Okay. So a hole at maximum, okay, material conditions go down, okay. You drill it and you got a hole. So that diameter is 6.25, and that's your smallest allowable size. Maximum material condition of an external feature, okay, outside. So it's kind of like you're just looking at a pen, okay? That's the external feature and the hole right there. And that is going to be 6.15, alright, inches again, diameter. And that would be the largest allowable size. So you wouldn't be able to understand right now, and you're like, what is it? I don't understand. Why I'm like getting this, internal feature of size, and I make a hole, and why is it got to be smallest allowable size? Because it is an internal. Yeah. Again, you're drilling, making a hole. Yes. It's got to be the smallest. Why? Because your hole can go bigger than that. Okay. So therefore, it will go over, in this example, 6.25 inches. Because if you put more force to make that hole, okay? So that's your more mass and your acceleration. So going down that way again. Yes. So in my previous slide, I already taught you, okay, about that drilling a hole going down. Can always go bigger if the force is bigger. Yeah, bigger and bigger. When you press it real hard, it's not going to be an ideal hole. It will be bigger than that. Try it. Go and get bored, okay? Wood or something, drill it, and you can see like, oh, bang. bang, bang, the more force you do, the bigger the diameter is. So therefore, okay, the hole at maximum material condition 4, again, here is your key point internal feature. It's always the smallest allowable size. Outside one, okay, so this guy right there. So we're looking at a pin in this example. A pin looks like that. It's a socle to that one, okay, it's external features. That pin, that is the largest allowable size. Can go over that. Why? Because we're dealing with an external feature, okay? It's not a hole, it's a socle thing, okay? A socle, a pin is a socle, little one. So anyway, so that's here is very, very big. It's 6.15 inches. So that's going to be your largest allowable, alright, size. And this is your diameter. Okay, now we're going to take a look at the mathematics. Okay, students they're so happy to go with math. They don't want to link with the physical thing. Okay, logic. Alright, so let's go here. So when you take a look at it, this is your tolerance. Okay, so our value measurement is 6.25, ideal one diameter, but you can go over, okay, 6.35, see, this is 0.1 over, that's nothing over, yeah, so 0.10 meaning like it can go to 6.35, so I go 6.35, and you cannot go down, okay, therefore 6.25. So your tolerance is going to be 6.25 and you can go up to 6.35. Okay. So therefore, when you take a look at the internal feature mathematically, okay, internal feature of size, the whole at maximum material condition, okay, is going to be the smallest allowable size. So when you go by the math, students usually try to remember this for the smallest allowable size. Okay, and that's 6.25 because you don't go to this direction. Okay, a hole, it's got to be again internal. Here's your key point. Internal is going to be the minus tolerance. Here in this case is 0, so therefore it's the same as 6.25 if you want to go by math. Alright, the second one, external. Here you have a set, okay, 6.15 inches and 6.05. And that's your tolerance, okay? Maximum material condition at external feature again. External feature. So we're going to take the largest one. So mathematically, student try to remember if that is external, is the top one, okay, which is 6.15, biggest one. If that is internal, the smallest allowable size, which is 6.25. And that is your maximum material condition. Maximum material condition. Okay. Alright, so I'm gonna erase it. But it's internal feature, if you want a maximum material condition, you're gonna choose the smallest tolerance, which is in this case 6.25. External feature, if you're looking for the maximum material condition, we're gonna choose right here the largest one, 6.15 in this example, right? So we'll go with mathematics, internal, external, external go largest, internal go smallest. Okay, regardless of feature size, RFS. So the material condition, when you think about it, we also have the condition that we think when we don't care about the feature size. Okay, it's just an implied, we implied that condition. Also, it indicates the geometric tolerance that applies at any increment of the size of the feature within its permissible limits. It also implies on all geometric tolerances, okay, unless indicated by the presence of a modifier. So every time we think about our FS, we have these, alright, implications. So one is that this is an implied, alright, condition. Second one, we're talking about the geometric tolerance. It's going to apply at any increment of the size, any increment of the size of the feature within its permissible limit. Okay. It also implies on all geometric tolerances unless indicated by the presence of a modifier. So if you think about the physical thing, we go back to that tolerance limit again, alright? So if we don't talk about this modifier for material condition, we're just looking at if you see RFS regardless of the feature size. We're just dealing with a regular, alright, limit for any kind of geometry. Any kind of increment of the size, okay? But then it got to be within the permissible limit. So meaning like your measurement got to be within here, unless otherwise it is indicated by your material condition, whether that's max or least, okay? Alright, so here is just the rules, but you don't have to remember any of it. All you have to know is how we how the rules look like and how we write it. That's about it. You don't have to remember any of this at all. So rule number one, we follow again this group which is called the ASME, right? And here this is just a code. Okay, you don't have to remember anything. Most of the rules come with a year and a section. Okay, so you go Y and then 14.5 go to this category M, alright, in 1994, way before you were born. And then section, go to section 2 and go sub 7 and then sub 107, right? So this is just like an address, alright, address of the root. So you go open that book, go to here, 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 and then go here, and then you can be able to read that. Okay, and that rule is perfect form at maximum material condition. So what does it say? Now this rule is saying rule number one is applied to all features and controlled by plus or minus tolerances. Meaning like anything that you want to measure, it's got to be in a particular tolerance or limit. Okay, you can't go over that to have some sort of a standard. So variation, okay, in form as well as size are allowed. So we're looking at the form, we're looking at the size. Okay, you can have the variation, however, it's got to be within that tolerances, which is indicated by plus or minus. Plus minus is just a direction on this side, on that side. You can flip it too, it doesn't really matter. What matters is that there's distance right there, okay? Rule number 2, go to section 2.8. It's saying like regardless of the feature size applies. Okay, we're dealing with whatever size there is with respect to the individual tolerance. Your datum, okay, that's a point, an axis, or the plane that reference or both, okay, where no more defined symbol is specified, right? But just here, rule number 2 is just we're dealing with any size, okay, and we're measuring from a datum. Then rule number 3 is, okay, applies to all the screw threads, gears, and the splines, okay, for measurement. So each tolerance of that orientation, or position, and data reference specified for the screw thread applies to the axis again. Well, if you think about the screw, there's got to be an axis, alright, of that screw to go in anyway. So of the threads derived from the pitch assignment there. So anyway, right now, all you have to understand is we have 3 rules, okay, in geometric tolerancing, and they are that it is controlled by ASME group. So if you're not familiar with ASME, okay, that's just American Society, okay, Mechanical Engineering. We are for your school, MSU, okay, for me is in industry engineering technologies. I come from Technology North College of Education, but I serve MSU under College of Education. So but then you are a part of industry. So industrial technology is a part of industrial engineering technology, where my line is, and that is a part of this mechanical engineering. Okay, so we have industrial engineering pure, and we have industrial engineering technology. We concentrate only in the machines of the industries. And then we also have mechanical engineering technology. Then we have electrical and so on. So okay. So the technology is a very new major, and they branch all engineering into engineering technology. Okay, that's our from our generation. So going into it, because we heavily use an incredible amount of machines, all right, to produce something nowadays. So anyway, so that's ASME, and what they do is they set the standard, okay, for the engineering. Everything to do with precision engineering is the part, okay, for metrology. They're all in one group. So anyway, so it branch out like that, and you have to study metrology. It's because you belong to industrial technology, okay, which actually is a part of our field, which is industrial engineering technology. So anyway, and going back here, we know what ASME, they set a standard. Every time they set the standard, there is rule to follow, and these are the rule to follow in metrology. Okay, you can't just go and measure whatever. You have to measure by the rule. Okay, so what are the rules? Rules are like that. And we heavily concentrate first one on material condition. Okay, second one is regardless of feature size, and the third one is your screw gears and splines. Okay, because they have different characters, so therefore you can mix the rules. Anyway, so that's about the rules. Let's go to the next one. Another one is you have to know the frame. Alright, we know the control. Yes, and the control come with the symbols. There are 5 types of control. Depends on the geometry of your measurement. And there are the tolerance. Okay, your measurement got to be within these tolerance, and you will obey. Okay, these symbols and telling you where to start to study, from which reference, from which data, and whether you have to be careful with the material condition. But we have a modifier right there. Okay, so max is right here, so therefore you have to choose the tolerance, the least one, the smallest one. Okay, and here it's telling you, okay, that's the diameter, and here, okay, it's telling you this is a position. All right, so just by looking at it, and I want you to go back to the table, and I want you to review the symbol, okay, what's this talking about, and the data here, okay, and understand that if we box them, all right, we call that the frame. So if I say feature, control, frame, I am talking about this thing, okay, that is the feature, control, frame, and it tells you information on how to do that measurement. So the very first compartment, so let me erase this for you. So the very first compartment is always contain the geometric symbol, okay? Geometry, so now telling me something right there. So if you don't understand what is this, go back to your table, take a look at your symbol, right? And then you will know your control type, yeah? Second one, so let's concentrate and frame on this slide. The second one is going to give you the tolerance information. So here you can see the value. That's my diameter, right? Include this, the shape of that tolerance zone. Okay, right here, the shape is totally circle right there. And then the tolerance value, again, is 0.3 given to you. And here is your maximum material condition, okay? That's telling you the tolerance condition. So that's your modifier maximum. So you have to choose the least, right? Out of your 2 plus or minus value, choose the negative one. And then A, B, and C. And then this A, B, and C is your third, fourth, and the fifth compartment. Because here 1, 2, this is 3, 4, and 5 compartments right there in our frame, right? So they're just, okay, giving you your datums, yeah? Datum, again, the measure origin of your measurement, from where you're going to end to measure, okay, whatever you're measuring. So it said, please measure from here, yeah? And you're doing this shape that much, and be careful with your material condition. Okay. So the first compartment, geometric symbol. Second compartment is this little one. It's going to be the tolerance information. We already know that. Yeah, and a cylindrical tolerance zone. In this case, diameter, that's solidified. The tolerance value 0.3. Okay. Parallel lines or parallel planes of uniform boundary of profile tolerance zone, tolerance value only. So if you think about, if we have like a parallel lines or planes or uniform boundary of profile tolerance zone, we're going to just put the tolerance value only. Okay. For cylindrical tolerance zone, we're going to put with the diameter. Okay. So the third component is all about datum, right? Datum. So reference portion right there. We have our primary, your secondary, and your tertiary datum right there. So now we go with the frame. So every time you think about the frame, you remember that there are 5 compartments, and each one of them is giving you an information. So what are they? They are that. Okay, and I want you to get it. Short-term symbol, value, whether you have modifiers or not. 3 modifiers right in there. We only show the first 2 because the last RFS doesn't have a symbol, right? And then we have 3, right? Datum, first, second, and third, which is your primary, secondary, and tertiary datum. Your measurements are going to come from these points, planes or axes, yeah. Okay, so that's for the first part.